Hello, welcome to the topic of automation for early detection of X-propagation in power-aware simulation verification. My name is Tony George and I am with Samsung Electronics. This is going to be a brief overview of challenges we faced during the UPF verification simulation and the solutions we applied, which is based on the automation and the left shift of the verification we could achieve. I would like to show you a quick glance of the results in the figure here. The top figure shows us our struggle. We had to complete the verification just in time, and the below figure shows the completion of the verification ahead of schedule. We will start with a quick introduction, just to ensure that we are on the same page. In a SoC design with multiple IPs, each IP can move between power modes such as power off, sleep, and power on. Depending on the power mode in operation, the independently powered regions of the IP, namely power domains, can be turned on and off. During such power on-off scenarios, retention cells need to be save memories and register values before the power is off and need to restore during wake-up. Each power domain can act its own. So it is necessary to ensure the power down IPs does not corrupt other IP functionalities. Hence, we have isolation cells that keeps the power of IP outputs in a predefined value instead of driving X values. Here you can see the power sequence necessary for each power domain, where it moves from the ISO enable to retention enable and to power off. Then to wake up, the power on to retention disable and finally to ISO disable. It is necessary the power sequence is executed correctly. To orchestrate these controls, there could be a centralized or a distributed state machine, which depends on the SoC architect. Generally, these state machines will be a part of the power management units, the PMU. As I mentioned in my previous slide, each domain can act by its own, which brings in the verification complexity. If there is a bug in any of these control signals or in the connections, we will end up having thousands of X values, which is really a pain to debug. Now, if we have a single X value occurred, it can propagate and gets distributed to thousands of signals within a few clock cycles. We also need to note that not all X values are unexpected. Some of them are valid because there can be valid X signals during the power down phase. Now, we have a mix of valid and invalid X values. The difficulty of root causing the origin of X signals starts here. When it comes to root cause analysis, the primary method we use is the waveform. But it can prove to be time-consuming because we are looking for a needle in a haystack. So it is necessary for us to find alternatives to the current verification approach. As many of us here already know, the X-propagation can happen due to multiple reasons. It could be the missing isolation cells due to the design issue, or it could be a missing control signal, which is another connection issue, or it could be a missing connection in the data signal, which is also categorized as a connection issue. Also, it could be a wrong power sequence control issue from the PMU. The traditional approach to verify the X-propagation is to simulate the functional verification test case until any data integrity checks are failing or the X value shows up in the output of the DUT. But by then, the X value is already propagated widely inside the DUT. So this approach adds delay in detecting bugs in power-aware simulation. Here, we also have to notice that we need to wait until we have a mature design to start the verification because we need the design to support data integrity. But to reach such a design maturity will also take significant design time. As shown in this figure, for each iteration of the bug, it took around 3 weeks. We have provided a detailed breakup in the paper why 3 weeks were taken for each of the cycle for the bug fix. Considering the slow verification process, we did a postmortem soon after the project is completed. This particular verification project took around 40 days, starting from the sanity clean RTL to the beginning of the synthesis phase. The figure here shows the number of bugs accumulated over time during the verification phase. Once the project was commenced, few bugs were detected at the early stage, which mostly belonged to the sanity test. After the initial bug finding, the detection of the rest of the bugs was slowed down, despite of our continuous verification efforts. As you can observe in this figure, most of the bugs were reported midway through the project timeline, and the bug trend was stabilized just in time for the sign-off. Obviously, it is not an ideal situation, so we had to consider improvements. Hence, our team re-evaluated all the bugs reported and the time taken for fixing those. Based on this analysis, the team concluded that we spent too much time in root cause analysis, and also bug detection was very late. Several proposals were made by the team, and one among them, the proposed solution was to insert checkers that to leveraging automation. Now, our plan is to have assertions and checkers automatically generated. The easy choice for us is to use the Python and write necessary scripts to generate the checkers and assertions. We can invoke our Python scripts from the same make file which is used for the compilation, elaboration, and the simulation. The invoked Python scripts will do the rest of the job. The figure here shows the automated generation of checkers and assertions in 3 stages. Let's get into the details. In the first stage, we need to prepare for the automation. One of the challenges in creating assertions is we need to know the RTL hierarchy so that we can bind our checkers and assertions into the right signals of the DUT. But there was no easy way to gather the RTL hierarchy. Also, the UPF file had minimal amount of RTL hierarchy information for our purpose. It turns out our elaboration log is a readily available source to gather the details of the RTL hierarchy. In our case, we use the cadence flow, and the elaboration log is generated in Xcelium. In the second stage, the file along with the UPF file is parsed to fetch the signal hierarchy that matches the power controls and sequencing. The UPF syntax is parsed and information on the power domains is extracted as an intermediate file. This file contains the information about the supply states for the power domains, isolation of inactive domains, memory retention, and its RTL hierarchy. Now we have essential information in the intermediate file, which we name as DHLF. In the third stage, the actual assertions and checkers are generated. The basic assertions and checkers are stored as template files, which will not have the signal hierarchy information and rest of the parameters. We have the code sections available in the paper related to these template files for your reference. From the DHLF file, the RTL hierarchy information is furnished into these checkers and assertion templates. The generated checker will be compiled along with the necessary assertions that will be included in the test bench. 2 types of assertions were generated and added to the checkers. The first type of assertion is the basic power flow. All signals going outside of the power domain. And the second type of assertions are for the retention cells. We also have 2 types of checkers to verify the isolation cells. The first one is to check if the control signals get toggled correctly in a power state. The second one is to check if the signals connected to the isolation cells are clamped to the expected values. Putting it all together, the Python will parse for the UPF syntax and the RTL hierarchy paths. Those are inferred from the elaboration log file. The assertions are then generated based on the template files. These assertions will be grouped into power, retention, isolation for generating the checkers. Finally, the generated checkers will be instantiated in the test bench as shown in this figure. Now, We have completed the development of the proposed approach, and it is time to check if the improvement actually helps. So we executed the same project with the additional environment. Just to make clear, this is just a pretend execution, not for the business purposes. One among the observation is at the early stage of the project, the number of checkers failure was very high, which enabled parallel debugging of each checker failure and finding multiple bugs in a single iteration. Another observation is the checker failure guided the engineers quickly to the right signals to look for. As a result, most number of bugs was identified at the early stage of the verification. You can observe that the rate at which the bugs were found in the figure here. So the bug trend is stabilized before the tape out. The conclusion is introduction of automation can left shift the verification process. Few additional benefits I have to mention is the reusability and scalability. The checker and assertion templates are prepared with reusability in mind. Hence, the effort necessary to set up this environment is the same for the future projects as well. When the number of power domain increases, the effort to set up the automated checkers will not also increase at the same rate. So that's how we save some effort in terms of scalability. With that, I would like to thank you for your time. My name is Tony George from Samsung Electronics. Thank you.